So today we're talking about percent yield. And the percent yield calculation is fairly straightforward. We said that percent yield is actually the actual amount that you get over the theoretical amount times 100. So that formula is fairly straightforward. You just plug things in. But usually when you have a percent yield problem, you aren't given the actual yield and you aren't given the theoretical yield. You have to do some type of calculation in addition to it. So here we're just tacking on one more step to the systems of solving equations that we've already done. Okay? So let's begin by looking at a problem. We'll pull out the information in the problem as we read it and put it on our chemical equation. And then we'll go ahead and solve that problem. So this problem reads, we've got 32 grams of methanol. Here's methanol. And so we've got 32.0 grams of it. And it reacts with excess CO. Here's our CO. So we have excess here. Right there, that's always a plus because that means we're not dealing with a limiting reagent problem. It's just a very straightforward problem. And it gives us our actual yield, which I'm going to write this in a different color. Actually, in the laboratory, we get 58.7 grams. Now, that's not our theoretical yield. That's what we actually got in the laboratory. So we have to differentiate the actual yield that we get from doing the experiment and what we calculate. Remember, the calculated one is the theoretical yield, and we know how to do that. So that's what this problem is really about. We have to get the theoretical yield, we have to calculate it, then we can plug it into this formula. Okay, so let's go ahead and look at that. In order to calculate the theoretical yield, we need to know theoretical yield is how many grams of this do we predict based upon the fact that we start off with this amount of our methanol. Okay, so we're just going to do bridge over troubled waters. Grams up to moles. Moles of one thing over to moles of something else, and then moles of that thing back down to grams. So remember, all the vertical ones are molar masses. All of the horizontal transitions are molar ratios. So let's go ahead and set this problem up. We have 32.0 grams of methanol, and I'm going to abbreviate it here so I don't have to write it all out. And the first thing we've got to do is change those grams into moles. We know vertical transitions are molar masses. To help us make this a little bit faster so that it all fits into one video, I got the molar masses pre-calculated up here at the top. And so here's our molar mass of methanol. And we've got grams in the top here, so where do grams have to go? They have to go in the bottom. So we end up with 32.0 grams of methanol per 1 mole of methanol. Our grams will cancel out. Now we have to go from moles of methanol to moles of acetic acid. Not a problem, we can do that. Our horizontal ones were molar ratios. So we've got moles of methanol on the top. So where do they have to be to cancel out? They have to be on the bottom. So we're going to put our moles of methanol here. We want to go to moles of acetic acid. So that's what I'm going to put on the top. Moles of acetic acid, I'll abbreviate it AA. Now the numbers that we put there, remember, are the coefficients of a balanced equation. We haven't checked to see if it's balanced yet. Number one thing to do, and we definitely need it before we use any molar ratios. So let's go ahead and do that. We've got a CH3 here, CH3 there. We've got another carbon. We've got two O's, and we have an H. So it is in fact balanced. It just happens that all of these coefficients happen to be 1. But do make sure you check that balancing. So the coefficient on methanol is 1. The coefficient on acetic acid is 1. The moles of methanol cancel. Now we have to go from moles of acetic acid to grams of acetic acid. And that's a vertical transition, so that's molar mass. We've got that calculated right up here. We have moles on the top, so we need moles on the bottom to cancel out. So 1 mole of acetic acid is 60.0 grams of acetic acid. Okay. We'll cancel those guys out. Now, the only units we didn't cancel out throughout this whole thing is acetic acid, grams of acetic acid. So our answer is going to be grams of acetic acid. We can go ahead and get our calculator and practice doing these problems. We've got 32 divided by 32 times 1 divided by 1 times 60 divided by 1. So actually our answer is 60.0 grams of acetic acid. That's theoretical. It's purely based on calculation. But we need that theoretical value in order to do percent yield, right? Alright, so let's go ahead and do percent yield. Down a little bit. So percent yield is our actual, which is the number that they gave us. They said we went in the library, they went in the laboratory and actually actually weighed out that this is how much acetic acid they got, this many grams. And we're going to put it over theoretical, which is what we calculated, 60.0 grams. And we're going to multiply it by 100. And go ahead and do that calculation. We get 97.8333, and of course our percent is our units. Now we look at significant figures. We had 3 here, 3 here. The ones are all exact, 3 here. So we need 3 significant figures. And so we go 1, 2, 3. Go to the one next door to see if we round up or down. That is a 3, so we're going to round it down. So we're going to get 97.8%. Okay. So, yes, the percent yield calculation is very simplistic. It's just a straight formula that you can plug into, but usually it's combined with a larger problem. So here we had to definitely know that we could do our bridge over troubled waters to get our theoretical yield. So we had the values we needed to do that percent yield. So look out for those types of things. Sometimes when they do percent yield, there's something you got to figure out before you can do that straight calculation.